introducing simulate time average coarse-grained molecular dynamics with geometric machine learning. Molecular dynamics simulation techniques have become an essential computational tool in many natural science disciplines, making massive progress across various atomic systems such as polymer, battery, protein, and membrane. However, many applications concern complex systems involve large number of particles and requires long simulation of nanosecond to microsecond level. Each long simulation is a sequential process that requires long wall clock time to finish. Moreover, we often face large chemical space in practice. High computational cost is a major limitation of MD simulation. To resolve the challenge of high computational cost and enable MD for higher spatial temporal scales, past work has studied techniques such as enhanced sampling methods that bias the potential energy surface, and coarse-graining models to reduce system complexity. ML-related efforts include machine learning force fields that learn to simulate MD from forces, and generative models that aim to sample from the state distribution. However, these techniques either do not produce realistic dynamics or are still not fast or accurate enough for many real-world MD applications. In this work, we resolved the aforementioned challenges of running large-scale MD using a different machine learning approach. First of all, we use spatial coarse-graining to reduce the system complexity. Secondly, instead of running the simulation at a time step of 1 to 10 femtosecond, which is typical for MD and coarse-grain MD, the ML simulator can run MD at a significantly larger time step at the nanosecond level by learning time-integrated acceleration from data without computing forces. In order to do large-scale screening, our model can be trained over short MD trajectories while being able to simulate long trajectories for novel unseen systems, and is orders of magnitude faster. First, we introduce how we coarse-grain an MD system. To coarse-grain a molecular system, we employ a graph clustering approach to group nearby bonded atoms into coarse-grained beads. The clustering process partitions the fine-level graph into roughly equal atom groups of a specified size, while minimizing the number of bonds with two endpoints in different groups. The corresponding bead embedding is the mean over the atom embedding. The weight is the sum of atom weights, and the position is the center of mass of the atom group. Graph clustering enables a consistent way to coarse-grain various systems at a specified resolution. The same approach can be applied to our battery systems for coarse-graining. In summary, we choose the coarse-graining level by adjusting the atom group size of the graph clustering algorithm for a given system, so important properties of interest are still preserved. Next, we introduce the temporal coarse-graining, large time integration. Spatially, we use coarse-graining. Temporally, we use a very long time integration step to speed up simulations. Given ground truth MD trajectories with femtosecond level time integration steps, we first apply coarse-graining to obtain the coarse level states. Then, we downsample to obtain a trajectory of lower temporal resolution with a very large time integration step. These time-integrated CG-MD trajectories will be the data that our learned simulator aims to model. Finally, we describe a workflow to tackle the challenge of large chemical space. Now that we have a machine learning simulator that operates under coarse-graining and large time integration, we can train and use it to screen a very large chemical space that is previously overly expensive to screen using traditional MD. We start by sampling short MD trajectories using traditional MD, which we use to train our model. The trained model can then be used to simulate other novel unseen systems in the large chemical space for very long trajectories, which are highly efficient with a nanosecond level time integration step. Long time properties of interest can then be computed from the learned simulated trajectories. Our learned simulator is based on graph neural networks, GNNs, a geometric machine learning architecture that is suitable to model 3D geometric data. Here, we demonstrate how to train our ML simulator. Given fine-grained level MD trajectories, our model first used embedding GNN to learn atomic embeddings, after which a coarse-graining model coarse-grains the systems by grouping nearby bonded atoms into CGBs. This is the pre-processing step that maps fine level system to the coarse level, where dynamics learning happens. Our model predicts the next step configuration based on history of k steps. The state history is featurized through a featurizer phi, and the featurized state representation is fed into the dynamic GNN and score GNN to predict the next step structure. The featurization step and prediction step together compose the CGMD simulator, which only operates in the coarse-grained level. The entire model is trained end-to-end by minimizing the next step mean square error prediction loss. Here, we color all trainable modules in blue and loss in red. The score GNN is a novel component we introduced in this work that is able to refine a potentially erroneous structure, thus resolving the long-standing issue of machine learning simulation becoming unstable when simulated for a long time. Our first experiment demonstrates our model's capability to simulate MD of single-chain CG polymers in implicit solvent, a representative material discovery setup with estimation problems involving long-time dynamics. The dynamics of the polymer is decided by its structure. The polymer conformation changes drastically through time. A representative statistics of the polymer geometry is the squared radius of gyration. It is defined as the weighted square distance to the center of mass. A single polymer's radius of gyration evolves and goes up and down. Intuitively, a higher radius of gyration means the polymer is in more of an unfolded state. The radius gyration therefore indicates polymer compactness, and is related to rheological behavior of polymer in implicit solvent. It also requires long simulation to estimate accurately. Here we show how the radius gyration varies across different polymer structures. We consider a challenge generalization task where we train on class 1, regular polymers, and test on class 2, random polymers. Note the irregular structure in the circled area compared to the class 1 polymer. We train on 100 class 1 polymer trajectories of length 50,000 tau, and evaluate using 40 class 2 trajectories that are 100 times longer. Here we show that using short empty trajectories of length used in training, the estimation of square radius gyration is of very high variance and error. We can use supervised learning ML models to directly predict the mean radius gyration, but with only short trajectories for training, the supervised learning models have to fit to noisy labels, resulting in prediction error. On the other hand, our learn simulator can predict accurately mean radius gyration, achieving an R-squared score of 0.9. This is because our model is able to fit the dynamics with short trajectories and generalize to long simulation and novel polymers. As our method simulates the polymer CG dynamics, we can also compute properties beyond the mean squared radius gyration. We find our model produce realistic trajectories that accurately recover the distribution of radius gyration and matching free energy surface under principal component analyses. Moreover, simulation from our model also recovers dynamical properties of the MD system, such as autocorrelation function of radius gyration. This dynamical property cannot be computed from independent samples of the system, and requires very long time simulation to reliably estimate. Our model shows good fit to the ground truth in the autocorrelation function, and accurately predicts the radius gyration relaxation time, which is derived from the autocorrelation function. To further demonstrate the effectiveness of our approach, we apply our model to a significantly more complex system, solid polymer electrolytes, SPEs, a type of amorphous material system that is promising in advancing lithium-ion battery technology. The battery systems contain thousands of atoms and are very complex. Our application involves screening a large chemical space where each SPE contains a distinct type of polymer. To study ion transport in these batteries, in particular particle diffusivity, very long simulation at tens of nanoseconds is needed due to its slow convergence. Here, the dashed black line shows the length of training MD trajectories, which is 5 nanoseconds. The particle diffusivity is far from converging at this point. We train our ML simulator using 500 MD trajectories of different SPE systems that are of 5 nanoseconds long, and evaluated over 50 testing SPEs using MD trajectories of 15 nanoseconds. We're only able to evaluate over a limited number of systems due to the high cost of simulating long trajectories. We aim to predict the lithium-ion particle diffusivity for various SPE systems, estimated using 50 nanosecond MD trajectories. Here, we observe that using short time simulation of 5 nanoseconds will lead to significant overestimation. Given only short trajectories for training, a supervised model still suffers from overestimation even with special treatment to rectify this systematic error. Recall that our model contained a coarse-grained refinement module to stabilize long simulation. Without this module, a learned simulator can render unphysical behavior and fail in predicting lithium-ion diffusivity. Our full model, the learned time-integrated CGMD simulator, is able to accurately predict lithium-ion diffusivity. Even though only short trajectories are available during training, the dynamics and the interaction of atoms don't change irrespective of the system or simulation length. Therefore, our model is capable of generalized to longer simulation horizon and novel SPE systems. The effectiveness of the coarse-grained on stability can be further demonstrated through the radial distribution function, RDF, computed from ground truth and learned simulation. Here, the ground truth RDFs are in orange, our learned simulator is in blue, and our model, but without the coarse-grained refinement module, is colored in red. We can observe that without the coarse-grained, the model can enter unphysical states and produce unrealistic RDF curves. Our full model with coarse-grained refinement module, matching ground truth on overall shape and peaks. Finally, the best part of our learned simulator is it is several orders of magnitude faster than traditional MD with classical force fields. Traditional MD requires tens to hundreds of CPU hours to accomplish one long simulation for the application we are considering. Our learned simulator can finish a long time integrated CGMD simulation with less than 0.1 GPU hour. In our paper, we also conduct ablation experiments to study the influence of our technical modifications, which you can find more details in our paper. To summarize, we present a machine learning time-integrated CGMD simulator that aims to learn the simplified dynamics using graph neural networks. Despite at a lower spatial temporal resolution, important properties of interest can still be extracted from the learned simulator. Being several orders of magnitude faster than traditional MD, our model can learn from short trajectories and generalize to long simulation for novel systems. The effectiveness is demonstrated through two realistic applications. We hope our work will advance the field of molecular dynamics by enabling simulation of long-time dynamics at large scale, bringing new insights through simulation that were previously too expensive to simulate. Please find out our paper and more details at our project website, shangfu.co/mlcgmd.